students, welcome to my second lecture on trees. Let us recall the definition of a tree. A tree is a connected graph without circuits or cycles. Now, what is a spanning tree? A subgraph T of a graph G is called a spanning tree of G if T is a tree and T includes all the vertices of G. Now, among the spanning trees of a graph G, the one which has the shortest length, shortest length is called as the minimal spanning tree. So, in this lecture we shall be discussing the algorithms to determine to find the minimal spanning tree of a given graph G. Okay. Now, suppose G is a graph whose edges are assigned lengths, that is are labelled with positive numbers, then T is called a minimal spanning tree of G if among all the spanning trees of G, T has smallest sum length or length sum. The sum of lengths of the edges of T is the smallest. So, we are going to discuss two algorithms by which we can determine the minimal spanning tree. Now, let us discuss first algorithm. This algorithm says that the input is a graph G with m vertices. We are given a graph G with m vertices. Let us order the edges of G by decreasing lengths, because the edges of G are labelled by positive numbers. So, we can order the edges of G by decreasing lengths. Now, proceeding sequentially, delete each edge which does not disconnect the graph until m minus edges remain. This is because if a tree is there with n vertices, then it has got n minus 1 edges. So, minimal spanning tree will have m minus 1 edges, because the graph G has m vertices. So, the minimal spanning tree will also have m vertices and will therefore have m minus 1 edges. Now, step 3 is output the remaining edges as they form a minimal spanning tree T of G. Now, let us see how we can apply this algorithm. Let us discuss a problem here. So, apply algorithm 1 to the labelled connected graph. We are given this labelled connected graph. The edges of this graph are labelled by positive numbers, positive integers. So, apply algorithm 1 to the labelled connected graph Q in the given figure to find a minimal spanning tree of G. So, we are going to find a minimal spanning tree of Q. Let us follow step 1. Step 1 says that order the edges of G by decreasing lengths. So, we can see which edge has got the maximum length. You see we have edge AF. Edge AF has got length 9. Then BC has length 8. Next highest. And then AC has length 7. Then we have B also has length 7, and then we have edge C which has got length 6. Then BF has got length 5. Then we have AE and FD which have got lengths 4 each, and then we have BD which has got length 3. And then so so we will arrange them in the decreasing order of their lengths. So, let us see how we can do that. See here, we see that graph Q has 6 vertices. Here we have 6 vertices A, B, C, D, E, F. And therefore, minimal spanning tree of this graph will have 5 edges. So, by algorithm 1, the edges are ordered by decreasing lengths and are successively deleted without disconnecting the graph Q until 5 edges remain. So, now AF has got the length 9, BC has got length 8, then AC has got length 7, B has got length 7, C 6, BF 5, AE 4, DF 4, BD 3. So, we have arranged the edges in order of their decreasing lengths. Now, let us see, we will start deleting edges without disconnecting the graph until only 5 edges remain. So, how we do that? So, we start with the edge which has got the maximum length. From here we start. So, deleting AF. If we delete AF, whether the graph gets disconnected. So, if we delete AF, okay, the graph is not disconnected. Okay. So, we delete AF. So, yes, then we delete, then should we delete BC? If we delete BC, okay, B and C, if we delete BC, the graph does not become disconnected. So, we can delete VC. Okay. So, okay, then AC, AC is, where is AC? This is AC. If we delete AC, the graph is not disconnected, and therefore, we delete AC. Okay. And then BE, BE, let us see, if you delete BE, okay, what will happen? Because we have already deleted AF, BC, AC. Okay. AF, this is deleted, AF, and then we have deleted AF, we have deleted AF, BC, AC, BC, BC we have deleted, and then we have deleted AC. Okay. So, we have deleted BF, we have deleted VC, we have deleted AC. Okay. Now, if we delete B, what happens? Okay. So, B and then E. Okay. If we delete B, what will happen? Okay. See, this is AC, means we have this figure after deleting AC. A, this is C, E, okay. Then we have AE, we have deleted AC, okay, and we have deleted VC also, and then we have B here, B here, okay. We have deleted A, okay, we have deleted AF also. Now, BD, BD, and we have BDDF. We have this. Okay. So, what we are doing? We are deleting, see, we have deleted AC. Okay. This is AC. We have deleted AC. We have deleted AF. We have deleted AF. We have deleted VC. We have deleted VC here. Now, if we delete V, okay, if we delete B, this one, then the graph, okay, becomes disconnected. So, we cannot delete B. Okay. So, this B remains there. Okay. It is not to be deleted, and then C. Okay. If we delete C, CE, okay. If we delete C, okay, what will happen? If you delete C here, then C will remain, okay. C will remain, and we will have like this, because deleting an edge does not delete the vertex. So, C vertex will remain there. Okay. So, we will have C here, it will become an isolated vertex. So, C, and then we will have this situation. So, it becomes disconnected, okay, and therefore, we cannot delete C. So, C cannot be deleted. Okay. Then we have in all 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 edges, and we have to delete 4 edges. So, that we get minimal spanning graph with minimal spanning tree with 5 edges. Okay. So, we have already deleted 3 edges, we have to delete 2 more edges. Now, let us see, can we delete VF? Okay. So, VF, yes, if we can delete VF, right. Okay. We can delete it, because a tree is in the tree there should not be any circuit or cycle. So, we can delete VF. Okay. So, will you, yes. So, we have deleted 4th edge now. Okay. One more has to be deleted. Now, we have deleted, yeah, we have deleted 4. So, now how many are remaining? 1, 2, 3, 4, 5, 5 are remaining. So, we have deleted with the deletion of this edge BF, we have in all deleted 4 edges, and therefore, the remaining 5 edges give us the minimal spanning tree, and that is the following. This graph, okay, this graph, okay, where we have deleted 4 edges, and the remaining edges are B, okay, B, C, this is C, and then AE, and then we have DF, and we have BD. Okay. So, it is the minimal spanning tree, it is a tree with 5 edges, and it is the minimal spanning tree, and the sum of lengths of the sum of lengths here, length sum is equal to 24, because we can see that what are the values assigned to B, C and AE, DF, BD. So, that we can see from here. Okay. So, B has length 7, B has given 7 and then C is given 6, okay, and then we are given AE with 4, okay, DF with 4 and BD with 3. So, this is 7 plus 6 13, 13 plus 8 21 plus 3, so 24. So, the spanning tree, minimal spanning tree has length 24 and it is shown in this figure. Okay. Now, let us apply algorithm 1 to this graph. Okay. Another example let us take, and we can find a minimal spanning tree of R. Okay. So, you can see here the 9 is the highest value, maximum value. Okay. So, EG will we are going to arrange them in the decreasing order, lengths in the decreasing order. So, EG will come, and after that EG we will have BD, because BD has 8 lengths. Okay. So, AC also has 9. So, AC, then EG, then BD, and after that D, okay, because it has 7 length, and then after D we have BC which has 6, and then B which has 6, then DF which has 5 and so on. So, we have this table, okay. AC with 9, EG 9, AB 8, BD 8, ED 7, BC 6, BE 6, EF 6, DF 5, CD 4, CF 4, DG 4. Okay. So, and now we are given the graph graph R with 7 vertices, A, B, C, D, E, F, G, 7 vertices are there. Okay. And therefore, for the minimal spanning tree there will be 7 minus 1, that is 6 edges. Okay. So, minimal spanning tree will have 6 edges. Now, how many edges are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Total 12 edges are there. So, we have to remove 6 edges, okay, by applying algorithm 1. Now, let us see how we delete the edges here. So, let us follow the algorithm. Okay. So, we will go on deleting edges in such a way that the graph does not become disconnected. Okay. So, AC, okay, we can delete AC. Okay. Let us see, we can delete AC, yes. Then EG, can we delete EG? EG, E and G, yes, we can delete EG, the graph does not become disconnected. And then can we delete AB? Let us see AB. AB. Okay. If you delete AB, we have already deleted AC. If you delete AB, then vertex A will become an isolated vertex. Okay. So, the graph will become disconnected, and therefore, we cannot delete AB. So, no. Then BD, can we delete BD? B here, B here and D here. We can delete BD, the graph does not become disconnected. So, yes. And then DE, can we delete DE? Yes, we can delete DE, the graph is not disconnected. Okay. So, yes. Now, BC, if we delete BC, we have already deleted AC, right. So, we are having this situation. If we delete BC, BD we have deleted, perhaps. Yes, BD we have deleted, right. So, what will happen? BD we have deleted. So, this is BD. So, this is A, B, but D we have BD we have deleted already. So, this will not be there. Okay. So, this is A, B. We have deleted AC, we have deleted BD. Okay. So, now the question is whether can we delete BC. This is your BC. Okay. BC, if we delete BC, we will have AC here, and then what we will have? We have already we have deleted AC, we have deleted EG, we have deleted AC. Okay, let us see, we have deleted AC, we have deleted EG, we have deleted EG, and then we have deleted AB. No, AB we have not deleted, BD we have deleted, BD. So, BD we have deleted, and then we have deleted DE. Okay. So, D we have deleted. Okay. Yeah. So, then what? Now, BC if we delete, what happens? Okay. So, BC if we delete, we will have this situation. Okay, BC if we delete, BC if we delete, we will have, suppose we delete this. Okay, we will have this situation, and we will have BE. Okay, B we have not deleted, B we have not deleted. So, we will have this, and then okay, CF is there, CF is there, and also DF we will delete later on. Okay, DF will be deleted later on. The question was whether BC can be deleted. BC, if we delete, that is this situation actually. Okay, see, if we delete VC, the two graphs become disconnected, because D has already been deleted. Okay, there is no, this D is not there. So, graph is actually like this now. The graph which is remaining is like this. So, if we delete VC, if this BC is deleted, the graph becomes disconnected, and therefore, VC is not to be deleted. Okay. So, VC can't be deleted, VC can't be deleted, and B can be deleted, BE. If you delete B, again the graph will become disconnected. Okay. So, because BC is there, right, BC is there. If we delete BE, if we delete B, then the graph will become disconnected, because E will become an isolated vertex. If I delete this B, I will have this situation. So, this is again disconnected. So, BC that cannot be done, we cannot delete B. Okay. So, this is also correct. Then FG can FG be deleted? FG can be deleted, yeah, FG can be deleted. Okay. And then DF. Okay. DF, now the situation is like this. Okay, we have deleted D, all right, and then we have deleted this one. Yeah. So, we can delete DF. DF is this. We can delete DF, and when you delete DF, what we get is the following. So, let us see. So, DF can be deleted. FG has already been deleted. Yes. So, this is not there. Okay. So, we have this, and we can see that this graph is not disconnected. Okay. So, we have altogether deleted 1, 2, 3, 4, 5, 6 edges, and so 6 edges are remaining, and therefore, the graph that we are getting after deleting the 6 edges is nothing but the minimal spanning tree. Okay. And minimal spanning tree has edges AB, then we have BC, we have BE, we have CD, and we have CF. Okay. So, these are the edges, and then DG, and their edges are labeled with numbers. AB is doubled with 8, BC is with 6, BE with 6 again, CD with 4, CF with 4, and DG with 4. Okay. So, 8 plus 6 that is 14, plus 6 that is 20, 20 plus 12. So, this is total length sum. Is equal to 32, 6, 8 plus 6 plus 6 plus 4 plus 4 plus 4. So, minimal spanning tree has these 6 edges and its total length sum is 32, and the minimal spanning tree is the following this figure. Okay. Now, let us discuss algorithm 2. Okay. This algorithm is based on arranging the edges by increasing lengths. In the algorithm 1 we had arranged them in the by decreasing lengths. Here we arrange them by increasing lengths, and so this is the step 1. We arrange the edges of G by increasing lengths, and then proceeding sequentially we add one edge at a time to the m vertices of G, such that no cycle is formed until m minus 1 edges are added. As soon as we have added m minus 1 edges and ensured that no cycle is formed, okay, the output will be the m minus 1 edges that were added, and they will form a minimal spanning tree of G. So, let us see, we are going to apply this algorithm 2 to the leveled connected graph Q in this figure. This we have discussed this graph we discussed earlier, and we applied algorithm 1 to this graph to obtain minimal spanning tree. Now, let us apply algorithm 2 to this graph and find the minimal spanning tree. Okay. So, let us again now this time we arrange the edges in order of their increasing lengths. Okay. So, we have this. Okay. So, BD, AE, BDF, BF, C, AC, BC, AF, they are arranged in order of their increasing lengths 3, 4, 4, 5, 6, 7, 7, 8, 9. Okay. Now, we have in all here edges are 6. Okay. Sorry, these vertices are 6. Vertices, number of vertices is equal to m is equal to 6. So, minimal spanning tree will have 5 edges. And number of edges. Number of edges in minimal spanning tree will be m minus 1, that is 5. Okay. So, what we go we go on adding edges till 5 edges are added, m minus 1 edges are added, and it is ensured that no cycle is or circuit is formed, okay, in that process. So, we see we have arranged them in the increasing order. Now, what we will do? Okay. So, see, proceeding add one edge at a time to the m vertices of G, such that no cycle is formed until m minus 1 edges are added. Okay. Yeah. So, so BD. Okay. Let us see where is B. You see we have B here. Okay. B, and we have D here. Okay. So, first step is that BD is added. Okay. BD is added. Okay. We are adding. Okay. BD is added, and then add one edge at a time to the m vertices. Okay. So, we are adding one the edge BD here, and then the second case is what? Second case is AE. Okay. So, AE. Okay. So, this is A here at the same level, A here and E here. So, we add AE. Okay. We have added 2 edges. We are to add 3 more. Okay. 3 more, right. So, then so yes, and then DF. Let us add DF. Okay. D and then F. If we add DF, so this is DF. Okay. DF, yes, and then now shall we add BF? Okay. So, let us see, if you add BF, a circuit is formed. Okay. So, we shall not add BF. Okay. So, no. Then CE, shall we add CE? CE, C is here. Okay. CE. So, we can add CE. Okay. All right. Now, we have 4 edges, one more is to be added, and so CE, yes. Then AC, if we add AC, what happens? If you add AC, okay, it becomes a circuit. So, we will not add AC. And then BE, shall we add BE? BE, okay, we can add B. Okay. Now, you can see we have 5 edges, okay, 1, 2, 3, 4, 5, okay, and the graph is a tree and without any circuits. So, it is a spanning tree, and by the algorithm it is the minimal spanning tree, because we have added edges in such a way that no cycle is formed until 5 edges are formed. Okay. So, this is the minimal spanning tree in this case, and you can see that CE has labeled with 6, AE is labeled with 4, okay, BE is labeled with 7, all right, and then BD is labeled with 3, and DF is labeled with 4. Okay. So, total length is 6 plus 4 10 plus 17, 6 plus 4 plus 7, that is 17, plus 3 20, plus 4 24. So, minimal spanning tree is formed from these 5 edges, and length sum is 24. So, this is how we reach the minimal spanning tree by applying algorithm 2 to this problem. So, this is the figure. Now, let us do this other example also. This we have discussed earlier, where we applied algorithm 1. Now, let us apply algorithm 2 to this problem. Okay. So, let us arrange them in the increasing lengths, in the order of increasing lengths, edges to be arranged in the increasing lengths. So, CD, CF, DG, DF, they are then BC, BE, FG, and then DE, then AB, then BD, then AC. They are arranged in the order of increasing lengths. Now, what we do is there are total how many vertices are there? 1, 2, 3, 4, 5, 6, 7 vertices. Number of vertices is equal to M is equal to 7. So, number of edges in the spanning tree, minimum spanning tree will be in the minimal spanning tree will be 6. Okay. Yeah. So, now let us add edges to the vertices of this graph G, and ensure that no circuits or cycles are formed until we have got 6 edges, okay, in the graph. So, okay. So, let us see. Yes. So, the first thing that we have to see is CD. Okay. Shall we add CD to the graph? Okay. So, C is here, yes, D is here. Okay. So, we add this CD, okay. And then after CD, CF, can CF be added? CF, okay, CF is here, right. So, CF can be added, okay, CF can be added, yes. And then DG, DG, where is DG? DG, okay, DG, yeah, DG can be added, okay. There is no circuit or cycle is formed so far. And then we have DF, DF. Now, if you add D to F, then we are seeing that CDF, okay, it becomes a cycle. So, we cannot add D to F, DF cannot be added, and then we, so this is no, and then BC, BC, okay. So, BC, this is BC, we can be, it can be added, okay. Now, 1, 2, 3, 4, 4 edges we have drawn, 2 more are to be added. Now, we, okay, so we have added BC, then BE, okay, shall we add BE? This is B. Okay, we can add BE. Now, okay, so yes, now, so how many we have added? 1, 2, 3, 4, 5, one more is to be added to this graph. Now, then we have FG, can FG be added? FG, if we add FG, sorry, if we add FG, you see what happens, this cycle is formed. So, we cannot add FG. Okay, so what we will do is FG cannot be added, okay, and then DE, can DE be added? If we add DE, okay, this is, if we add DE, then it becomes a cycle. So, we cannot add DE. So, no, it cannot be added. Okay, now what we have, okay, so D cannot be added. Now we have AB, 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 okay, so AB is this. Yes, we can add AB and we can see now we have in all 6 edges 1, 2, 3, 4, 5, 6, okay, and the no circuit is formed, okay, and therefore, so we stop here, okay. We have got the minimal spanning tree and the length of this spanning tree is 8 here, then we have BC, BC is 6, okay, B is 6 and then DG, DG is 4 and we have CF, CF is 4 and we have CD, CD is 4. Okay. So, 8 plus 6 14, 14 plus 6 20, 20 plus 4 24 plus 4 28 plus 4 32. So, length sum is equal to 32. Okay. So, we can draw the minimal spanning tree by applying the algorithm to here in this case. So, we have got the sum length equal to 32 and we have this figure of the minimal spanning tree. So, that is all in this lecture. Thank you very much for your attention.